transform to a butterfly? We can make a guess based on the initial state and the end state. Calculation can be terribly wrong. However, if we watch the dynamic processes directly, there's no ambiguity. In material science, they are full of processes that involve materials transformed from one state to another. To understand those problems, including the material's properties, it is important we study the material's transformations directly by direct observation. As a material scientist, I'm interested in a variety of materials and materials processes in applications for sustainable energy and clean environment. I study materials at the atomic level. Scientists using telescopes to study the large matter, like stars, galaxies. I use a transmission electron microscope to study the smallest matter, the atoms. Transmission electron microscope is a very powerful tool. Even President Obama was amazed by the atoms that can be visualized using a transmission electron microscope. A transmission electron microscope can use the high energy electron beam and focus the beam using a series of magnetic lenses in high vacuum for imaging. As a comparison to a light microscope, the electron microscope has much better resolution to see small things, atoms, because the electron beam has very small wavelengths. In conventional imaging, using a transmission electron microscope, because of the high vacuum environment, we image materials by drying them out or freezing them. Then, to understand how materials transform from one stage to another, we have to do the extrapolation, just like to make a guess on how does the caterpillar transform to a butterfly. Recently, I developed a liquid cell, as shown in this schematic. It can isolate the liquid from the high vacuum environment, so I can study samples, can study materials using the transmission electron microscope. Over the years, my students have made several versions of liquid cells. Here I'm going to show you, using the liquid cell, what we can see that was never before possible. This is a movie showing you the growth of small platinum crystal in liquid. You can see majority of these crystals developed into cubic shape. We can also have a closer look at one of these particles. We can see how it developed into a cubic shape. As it rotates at certain angle, we can see the atoms line up. It's really amazing. By direct observation, we found the 100 years old theory for crystal growth is not correct. We found a new rule for the growth of these small particles. Using the liquid cell, we can also address questions in real-world issues such as batteries. We can make a small battery cell by putting electrodes inside a liquid cell. Then we can monitor the electrode-electrolyte interfaces during charge and discharge using a transmission electron microscope. Then we can see how does the battery work. Mostly, how does it fail? As we're all familiar with the problem, as your cell phone ages, the battery does not take a charge as well. Here is an example. We can image this formation of dendrites during charge and discharge. This damages the battery. If we understand them better, we can make better batteries. Using the liquid cell, we can also image biological materials in natural water environment. In summary, using liquid cells, we no longer have to guess how materials transform. We can directly observe material transformations using a transmission electron microscope. This is going to advance our understanding of materials, help us to solve world important problems. Thank you.